Alright, hello and welcome to lecture 21. We're going to talk about recursion this week, and this is probably, in my opinion, the hardest topic in this class. So I put an extra skull here. Definitely pay attention. I'm going to try and make it fun and exciting and enjoyable, but it is a difficult thing and it might take some time to sink in, just like for pointers. Okay? So let's get started though. I'm going to make it make sense. I'll try my best. So let's go. All these pictures that I included today, they're kind of giving you an idea of recursion. So there's some sense of repetition, there's some sense of things getting smaller. That's what I want you to have in the back of your mind. Like you have this triangle, but hey, that triangle's also here, zoomed in, but that same triangle's also here, zoomed in, but it's also here and here and here and here. What? Then you have these dolls. You have smaller versions of them inside of themselves, and then this picture is fun. It is a picture of a woman holding, I think this is like maybe like a tin of either tea or coffee, and the woman is holding the tin with her on it, and so it zooms in forever. So that's a general idea of recursion. So let's talk about what recursion is not first. So up until now in this class, we've been using iteration to solve problems. If I could spell, repetitive problems. And every time you hear the word iteration or iterative, iterative solution, I want you to think loops, okay? You got your while and for, etc. That's iteration. Recursion is something else. Recursion, this thing that I'm trying to teach you, we're going to get there, don't worry, is like loops without using loops. It's weird. Let me give you an example of it. So this is the standard example that I like to give. It's factorial, because we all know what factorial is. So recursion, I'm going to define it now. Recursion is the process of solving a problem by using smaller versions of itself, smaller versions of that problem, that same problem. You build up the answer using those smaller versions. Okay, that is the basic idea of recursion, and so let me give you the factorial example now. So, factorial. What is 5 factorial? You remember this from math class? What is that? Write it out. Take a second. Well, I think you remember that it's 5 times 4 times 3 times 2 times 1, right? Okay. Now, I'm telling you that factorial is a recursive problem. It can be solved recursively. So, I want you to find a factorial inside of a factorial. Can you find a smaller factorial inside 5 factorial? Question mark? That's funny. Take a second, pause the video, see if you can find it. Well, assuming you're back, you might have found this one, 4 factorial, or 3 factorial, or 2 factorial, or 1 factorial. They're all there. There's 4 factorial, there's 3 factorial, there's 2 factorial, there's 1 factorial. They're all inside of 5 factorial. And the most useful factorial for us is 4 factorial. The next smallest factorial, the next smallest sub-problem for the factorial problem is 4 factorial. Oops. So do you see how you could build up 5 factorial using 4 factorial? That's funny. It thinks that was the end of a sentence. And question mark. Well, it's 5 factorial is 5 times 4 factorial. That's quite nice. Okay. This is all fun. We found a smaller factorial inside of a bigger factorial. What does that buy us? Well, that's actually a way to solve this problem. So let's talk about those things. So 5 factorial equals 5 times 4 factorial, yes? But what is 4 factorial? But also 4 times 3 factorial. And what is 3 factorial but 3 times 2 factorial? Etc., 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 on and on and on. I can use that same pattern to solve 4 factorial. 4 factorial equals 4 times 3 factorial. So in general, we found a rule. In general, n factorial equals what? N minus 1 got ahead of myself. N factorial equals n times n minus 1 factorial. You see that? Just do it like this. N times n minus 1 factorial. Isn't that cool? That's quite nice. N factorial equals n times n minus 1 factorial. This is called the recursive case because you're using a smaller subproblem to solve the bigger problem. Does that all make sense? So I could plug 5 factorial into this formula, and I will know that, oh, yeah, 5 factorial equals 5 times 4 factorial. And now I'll just worry about solving 4 factorial. It's a smaller problem. Eventually, I'll get down to something I can do. So the issue right now, the issue with just using the recursive case is you never stop. It needs to be paired with some kind of stopping condition. Like the problem gets so small that you can immediately solve it without using smaller subproblems. Because right now, given our definition, what we're trying to do, we'll do this. We'll be like, oh yeah, 2 factorial equals 2 times 1 factorial. And oh yeah, 1 factorial is 1 times 0 factorial. That's actually defined in math. And this was like, oh yeah, 0 factorial equals 0 times negative 1 factorial. And that one, well, that's negative 1 times negative 2 factorial. Do you see where this is going? On and on and on until the end of time. We need to stop. We need this to stop somewhere. And where do we want this to stop? Probably either right here or right here. Okay? We need to stop here. We need to stop that process of trying to solve a smaller problem. Okay? And that's called a base case. Is a stopping condition for a recursive problem. Because your end goal is you're trying to solve a problem in terms of itself, in terms of smaller subproblems. Eventually, you're going to get down to the smallest problem that you can immediately solve and then build the solution back up. Okay, a base case is a stopping condition for a recursive problem, so our base case should be 1 factorial. That's immediately 1, okay? So now with these two rules, we can solve any factorial question. We can solve the factorial problem. Okay, so let me make a blank slide and let's recap what we have noticed. So we've come up with two rules. Our first rule is the recursive case for factorial. I do not want any design ideas, thank you. This is the factorial. We got our recursive case where we notice that n factorial equals n times n minus 1 factorial. And then we have our base case where you could either use 1 or 0 factorial for this example, just to not confuse you extra. I'll say that 1 factorial, that's defined to be 1 in math. Okay, so with those two rules, we can solve all the factorial problems. So you give me 5 factorial, I'll use rule 1, so this is rule 1, to break it down into, oh yeah, the answer is 5 times 4 factorial. Sure, you got it. And then we just need to worry about this smaller problem now. So we're like managers. We're giving problems to our to people who are under us. And what's 4 factorial? But 4 times 3 factorial, using again the recursive case. And what's 3 factorial? But 3 times 2 factorial. Okay. And what is, again using the recursive case, what's 2 factorial but 2 times 1 factorial? And then finally, we're going to stop because we notice that we're at the base case. What is 1 factorial? Oh, that's 1. That's the final answer for that one. You see that? And so now, finally using the base case, we've stopped. Stop and build up the answer. Okay, so we see the 1. It's like, oh yes, the answer is 1. So we go backwards now. Like, oh yes, I was waiting to multiply 2 by 1. Boop. 2 by 1 factorial, the answer is 1, so the answer is now 2. And this one's like, oh yes, so the answer for 2 factorial is 2, so my answer of 3 times 2 factorial is, 6. This one was waiting for 3 factorial, and now it knows that 3 factorial is 6. We can give back the answer of 4 times 3 factorial up here. We're like, oh, yeah, that's 24, right? I can math. And then this one can finally give back its answer of 24, because that was what 4 factorial was, times 5, which is, I'm not entirely sure. It's close to 100, right? That's what computers are for. 120. That's the final answer. So we shoved smaller and smaller problems on ourselves until we came up with an answer that we could immediately solve. Okay? That's the gist of recursion. So what I'd like to do now is show you how to write this in code. Show you how to solve the factorial problem in code. Okay? So normally we solve a problem by writing a function in C++, or like a big class around the problem. So a recursive function is a function that's going to call itself on a smaller version of the same problem. Okay, so we're going to say, get ready. How do we translate our base case and recursive case into code? We're going to say, inside of the factorial function, the recursive case, we'll say return fact n minus 1 n times fact n minus 1. That is code. We are inside of the fact function, we're implementing it, but we're calling it on itself. What? And then the base case is going to be return 1 if it's 1 factorial. Okay? So that is going to be our function. Let's make this happen. So let's see out fact of 5 and then fact. Now fact of 5 is probably fine. Yeah, let's make this work. Int fact, int n. So this is the function that returns n factorial. So you give me an n, I'll give you back an integer that is n factorial. Okay? So here's how you program this recursive problem. Here it is. We start with the base case and the recursive case. So we need to notice if we're called with 1, in which case we're in the base case. If n is 1, we're trying to solve n factorial. We're trying to solve 1 factorial. That's just 1. Return 1. Else, hopefully the user didn't give us a negative number or 0. This will be the recursive case. N factorial equals n times n minus 1 factorial. Okay? So we'll say return n times n minus 1 factorial is just this function again, called with n minus 1. What? And now I'm going to run this and potentially blow your mind. We get 120. And this is exactly the same thing. It's doing the exact same thing as the iterative version. So I'll say int fact iterative, int n. That one you can do with a loop, of course. Iteration involves loops. So I'll say dun dun dun. How about int result starts at 1 for int I equals n. I is greater than or equal to 1 I minus minus. Then we'll say res equals res times I, return res. This should in theory do the same thing. So now, what I'm trying to tell you is you have options. They both do the same thing, but now you have options. You have another way to solve this problem. And sometimes it's easier to solve a recursive problem. Yeah. Okay. I think that's where I want to leave you there. And let's talk about now why this translated to this code works. Okay? And that's going to bring us back to stack diagrams. So it's going to help you learn how to believe in recursion if I draw the stack diagram for how that fact function works. So let's look at fact 5, how it looks on the stack when it was called. Okay? And that will help us understand recursion. So I like blue better. So from main, this is what we did. From main we called, fact of 5. Okay, so that's what's going to happen. From main we called fact of 5. And now let's run this. So main called fact of 5. Fact of 5 is running. So we jump up here with n equal to 5. It's not 1, it's not our base case. So we're going to hit the recursive case, and we're going to say, all right, the answer is n times fact n minus 1. So we have to go off and compute fact of n minus 1. So fact of 5 needs to wait for fact of 4 to get computed. So fact of 5 called fact of 4. You see that? And fact of 5 is still waiting to run. It needs the answer from fact of 4 before it can multiply. Okay? And again, fact of 4, it needs to multiply 4 by fact of 3, so it's going to call fact of 3 and wait for it. Same with fact of 3, going to call fact of 2, wait for it so it can multiply its 3. And then finally, fact of 1 is going to get called because fact of 2 hits the recursive case one more time. Oh, sorry. I can't think and write at the same time. So we finally hit the recursive case because fact of 2 is going to call, well, it's 2 times fact of 2 minus 1, which is 1. And finally, fact of 1, we hit the base case. And it's like, oh yeah, dude, I got this. I don't have to do anything else. My answer is 1. And it returns. So control comes back to fact of 2. It got the answer. Oh yeah, fact of 1, it's 1. So it's going to multiply its 2 and return that answer, 2 times that. And so fact of 2 is going to return 2 times 1, so 2. Fact of 3, and now it's fact of 3 at the top of the stack. Its fact of 2 is done. It's returned. It's returned its 2. Fact of 3 was waiting for fact of 2 to multiply its 3 by the answer. And so it'll multiply 3 times 2, so it'll give back 6 to whoever called it. And fact of 4 called fact of 3, waiting to multiply its 4 by fact of 3. And we got the answer. 4 times 6 is 24. And fact of 5, the initial call to fact, was waiting to multiply its 5, because that was what n was initially, by n minus 1, which was fact of 4. And oh man, we did a whole lot of work to calculate the answer for fact of 4, but we know it now. So we'll just multiply our 24 by 4 and get back 120. And that's what main wanted, so that it could see out 120. Okay, and these all returned. Now it's just main running again. Okay, so fact of 5 calls fact of 4. Fact of 4 calls fact of 3. Dot dot dot. Fact of 2. Oh shoot. Calls fact of 1. Fact of 1 doesn't have to do any extra work. Fact of 1 returns 1, and now the stack unwinds, we say. To compute the bigger answers. So fact of 5 was waiting on fact of 4, who was waiting on fact of 3, fact of 2, fact of 1, and finally it's all going to bounce right back, calculate all its final answers. Okay? So that is probably still very confusing, and I'm going to give you plenty of examples to try and make it less confusing, but this is a very difficult topic. It took me years to fully understand recursion, I promise you, so do not feel bad. But I'm going to try and get you up to speed as much as I can. So the last thing, well, not the last thing, but the last thing about Factorial, I guess, that I want to talk about is just a general proof of why recursion works, and I'll use maybe Factorial as the example. So we're going to get a bit mathy, so I'm sorry if you don't like math too much, but it's not like calculation, it's more like theory. It's logic. So let's pretend that we're trying to solve a problem P. In your mind, just pretend that P is fact, okay? Pretend P equals fact. This is why recursion works, okay? Because you build back solutions up from the bottom. So pretend that we're solving some problem P. You have to give a base case, and the base case is essentially you saying that, hey, I know how to solve P of 0, the smallest problem, okay? Smallest problem. Be like, I know how to solve it. And then the recursive case is saying, all right, you give me the answer to a smaller problem, I can build up the bigger problem's answer using that. So if you give me P of k, if you can solve the problem for 1 smaller than my k plus 1, then I will be able to solve the bigger problem. So you give me a smaller answer, I can solve a bigger problem. So there's like an arrow, sorry, not error. If you give me a solution to 1 smaller of a problem, I can solve the bigger problem. And this is why recursion works. Because you asked for P of 5, is there a way using these rules to build up P of 5? Well, sure there is. Because you can start with P of 0, and you can use, well, that's the first rule, and then you can use the second rule to build up larger answers. Like, oh, okay, this one was looking for, if it had a smaller answer, it can make a 1 bigger answer. And that's the recursive case. That's what it's doing. I can use that to get P of 1 from P of 0. I just plug in P of 0 into that, set k equal to 0, and suddenly I have an answer. And I can use P of 1 to get P of 2, which I can then use this rule again from P of 2 to get P of 3, to get P of 4, to get P of 5. Okay, so the idea is, like, if somehow magically I had a smaller answer, I could use that to build it up. Build up the bigger answer, and also you have the smallest answer. This means, taken together, these rules taken together, can solve any problem. Okay, and I hope you see that. You can use P of 0 to get started, and then use this second rule to build up as big of a k that you want to solve, as big of an n as you want to solve. So you can solve factorial for anything. And that's beautiful. And now I need to show you the magic as well, because that's how we think about problems. So this is how I want you to think about these problems eventually. Here's the magic of recursion. You get to assume that the recursive call on the smaller problem worked correctly. When you're implementing the recursive case, this is the base case. This is the recursive case. When you're implementing the recursive case, you get to assume that the recursive call worked on the smaller problem, as long as you build up the bigger problem's answer correctly. Because it will be correct. Eventually it'll get down to 0 and it can build itself up. That's the reason why. It will be correct. It'll hit the base case and start building itself up correctly. So you get to assume when you're implementing that, oh yes, just assume that this worked. Assume that this gives me n minus 1 factorial. How do I build up the bigger answer using n minus 1 factorial? Oh, I'll multiply my n by that. That's beautiful, isn't it? So you get to assume. You don't have to think without thinking. That fact n minus 1 correctly computes n minus 1 factorial. All you have to worry about is building up the bigger answer. So that's a beautiful thing, and I think I just want to give you a bunch more examples now to just drive that point home and just get recursion ingrained in your minds as much as I can. So let's start with the power function now. Okay, so the power function, that's what POW stands for, is going to do the following. It's like, all right, you give me 2 numbers this time, not just 1 like factorial. You give me 2 numbers, like an x and a y, and compute x to the y, where y is an integer. Okay, so that's what we want to compute. So, like everything I'm going to say in this lecture and the next one, okay, x to the y, oh shoot, let's do it like this. How about x to the y? That's what POW is. Let's write it like this. It's hard to find POW x to the y. That's what we want to compute. Alright, should compute it. So can you find me a smaller power computation inside of a power computation? So let me give you an example. So let's pretend it was like, I don't know, 2 to the 4. So write it out. What is this? 2 times 2 times 2 times 2. Can you find me a smaller power computation inside of this? And I think you're probably getting the hang of it by now. Assuming you've unpaused the video, the next smallest power is 2 to the 3. So you can write this recursively again. You can say, all right, what is x to the y but in x, 1 extra x times x to the y minus 1. You see that? That's beautiful. So that's the recursive case. I'll say RC for recursive case. And then what's our base case? Eventually, we're going to be like, oh yes, 2 to the 4 is 2 times 2 to the 3, which is 2 times 2 to the squared. Well, that 2 squared is 2 times 2 to the 1. That 2 to the 1 is 2 times 2 to the 0, and that 2 to the 0 is 1. That can be our base case. That's when we want it to stop. We don't want it to be like, all right, what's 2 to the negative 1? We don't want to go that far. The base case should be, all right, anything, any number x to the power of 0 is always 1. Okay? That's our stopping condition. All right. So base case stops the powers computation. It's a very small power, so anything to the 0 power is 1. And the recursive case builds up the bigger answer using a smaller answer to the same problem. Okay, so here is me implementing it, and I'm gonna talk how I want you to think. So I'm gonna make a file called pow.cpp, and oops. And so what I want you to think about is like, all right, cout pow 2 to the 4 new line, which should be 2, 4, 8, 16, right? Okay. Int pow, int x, int y. This should compute x to the power of y. I guess this could be a double, actually. The x could be a double if we wanted it to be. But the y has to be an int. Okay, so the base case we figured out. Like the stopping condition, you just have to program that. It's like, okay, if y is 0, return 1. I'm going to be all cool and not use braces. Else, now here's how I want you to think. All right, x to the y, assuming I had x to the y minus 1, how can I build up the bigger answer? So, assuming I had x to the y minus 1, how could I use that to build up x to the y, the biggest answer that I was supposed to calculate? So I gotta do some extra stuff here involving that. Okay? And the reason that this works, again, is you just get to assume. Like, assume you have this smaller answer, build up the bigger answer correctly. By the power and magic of recursion, eventually it's going to go down to the base case and build itself up using your correct rules. Alright, so the answer is, alright, this is going to give me x to the y minus 1. Using math, I just have to multiply by an x and I'll have the final answer. Bam, I have a working, correct power function. Oh shoot, what have I done wrong? Result unused. Oh, sorry, it's return. That's why it's unhappy. So else return this thing. And again, I'm not using braces because there's just one line as the body. All right, so now we're doing pow. Bam, it's 16. And let's talk about why it works one more time. Then I'll stop doing this. So it's working its way down, building itself back up. By the magic of recursion, you can just trust that. But if you don't trust it yet, here's why it's working. Here's how the stack is working. We're saying from main, saying pow 2 to the 4. It's like, okay, I need to compute 2 to the 4. I'm going to multiply 2 by 2 to the 3. So let's go and compute that. It's like, oh yes, I need to multiply, I need to take 2 to the 3. X is 2, y is 3. It's not the base case, so I'm going to multiply my 2 by 2 to the 2. I'm going to go off and wait to compute that. And 2 to the 3 needs to wait for that to be finished, just like 2 to the 4 is waiting on 2 to the 3. It's just a waiting game right now. It's like everybody going into the DMV at the same time with the same problem. So 2 squared is then going to work on, because it needs to, it notices that, okay, 2 squared is 2 times 2 to the 1, so it's going to go off and recursively compute 2 to the 1. And then that's going to hit the base case eventually, because this is the last recursive case. Okay, 2 to the 1 is 2 times 2 to the 0. And then anything to the 0th power, we've discovered is the base case. We're going to return 1. The answer is immediately 1, no extra work. Bam, give back 1, return. Bam, I was waiting on that to multiply my 2 by the answer, 2, return. Oh, I was waiting on that to multiply by 2. 2 times 2 to the 1. 2 to the 1 was 2. 2 times that, 4. Return. 8. Return. 16. Back to main. That's what we wanted to print. Okay? It's nice to see how it's like building up the stack and then unwinding it. It's doing the fancy math. It's going down to the base case, going down to the base case and computing p of 0, and then it's using your recursive case to correctly solve the bigger problem, one at a time. It's building it up. Okay, so just like you could have infinite loops in non-recursive functions, in an iterative solution, you can have some fun. There's a special new kind of error that you can get now. It's called a stack overflow. It's when your stack gets so big. Remember I told you that the stack was fighting with the heap? Like the stack was growing this way in its little portion of memory that it shared with the heap. And it's only got so much room. Eventually, you're going to keep calling so many functions, like if it's an infinite loop, it's going to blow, it's what's called blow the stack. So it's going to overflow. The stack gets so big that you run out of memory. Because each stack frame, remember, it's got to store all the parameters, all the local variables. I'll call those local / where to return to. So there's actual memory going on here. It's like, okay, yeah, pow 2 to the 4, it needs to remember to go back to main, like that's who called me. Whereas pow 2 to the 3 needs to remember, I need to go back to pow again, that's who called me. So there's things going on. It needs to remember the 2 and the 4 here, the 2 and the 3 here, the 2 and the 2 here, etc. So it's taking up memory, and each stack frame takes up memory. So eventually you can run out of memory if you have an infinite loop. So the easiest way to have a stack overflow is to have no base case. Because then that will cause things to go on forever. It's like, okay, yeah, what's 0 factorial? Oh yes, 0 factorial equals, that's just 0 times -1 factorial. Oh, what's -1 factorial? But, oh, that's -1 times -2 factorial. And then it just goes on and on and on until the end of time. So if you forget a base case, it's going to keep on trying the recursive case, and it doesn't know when to stop. And this is why it's very important that your solution gets smaller. If you have a recursive case that never makes progress towards the base case, it's like, oh, what's n factorial? Oh, that's just n factorial. It's like, okay, yes, return fact of n of that same n. That's never going to get anywhere. Okay, so those are my two ways to have a Stack Overflow, and let me show you that happening. I'm probably going to crash this virtual machine when I do it. We'll have some fun. So I'm going to comment out this base case and this else, of course, because now it's just one line. I'm going to have just a recursive case. I'm just going to keep on trying to calculate the power of 2 to the something. 2 to the 2 is going to call 2 to the 1, is going to call 2 to the 0, is going to call 2 to the -1, going to call 2 to the -2, just on until the end of time. And beautiful. Okay, it didn't crash my computer. I'm very happy. So it's going to get a seg fault for a weird reason. It's going to run out of memory, and it's going to try and put the stack in a weird place of your program. It's going to like try and put the stack up here in your globals. Up above that, it'll probably work there. Up above that is like the text of your program, which is read-only, remember. Read-only. This is all technical, you don't have to remember this, but it's going to try and modify the code of your program, and that's where it's going to have a seg fault, because it's like, oh, that's read-only memory. Seg fault. So remember your base case. And remember to make progress. It's like, oh yes, what is pow xy? But x times pow xy, so this is incorrect, of course. So the recursive case makes no progress. It doesn't get smaller. Another seg fault, because it's going to blow the stack. All right, back to normal. Hopefully that makes sense. You can have runaway programs in a new way now with this thing called a Stack Overflow. And I'm sure you've used stackoverflow.com. And this is where they got their fun name. Now you know. Okay, let's see. Let's see where I'm going with this. Let me start Fibonacci, and then maybe we'll talk about why it's slow next time. So let me teach you about this fun sequence called the Fibonacci sequence. Here it is. This is a point of contention over mathematicians whether or not the sequence starts at 0 or 1, but let's pretend it starts at 0. Fibonacci sequence is a mathematical sequence that starts with 0 and then 1, and then it goes 1, 2, 3, 5, 8, 13. Yeah, 13. 19, 20, 21, 21. On and on and on. And the trick is, this is how it works. 0, 1, 1, 2, 3, 5, dot, dot, dot. Maybe you read about this in your book already, who knows. But it's still a fun little thing. It needs 2 starting points, but after that, the next number is always the sum of the 2 previous numbers. So this 1 comes from you adding 0 and 1. That's 1. It's 0 plus 1. And so this 2 comes from you adding the 1 and the 1 together. That's 2. And therefore this 3 comes you adding the 3 and the 1 together. Always the 2 previous elements. So the next element in the sequence is the sum of the 2 previous elements. And eventually the ratio between the two consecutive sequence elements is like it approaches the golden ratio. Maybe I'll show you some fun examples of that in the next lecture. But this is all you need to know to get started. But oh man, let's pretend we have a function. Let's write a function. We want a function fib of n to calculate the nth Fibonacci number. Let's say that this is like the 0th Fibonacci number. How about that? So this is the 0th Fibonacci number. So fib of 0 would return 0, fib of 1 would return 1, fib of 2 would return 1, fib of 3 would return 2, fib of 4 would return 3, fib of 5 would return 5, and so on. So we want to write a program that does this. We want to write a function that does this. Can you see a recursive case? So if I have, and I'm trying to calculate fib of n, how do I use smaller fib solutions to calculate that? Like if I'm at fib of 5, what is fib of 5? But how do you get these in terms of fib? It's that plus that. Oh shoot, it's fib of 3 plus fib of 4. Those are smaller calls. It's making progress. Oh heck yes. We got this. Fib of n equals fib of n minus 2 plus fib of n minus 1. Oh yes. That's the recursive case. What's the base case? So you can go all the way down to this one, and you can build it up with these two. But it's incorrect to just say that the base case is, oh yes, fib of 0. That's 0. Because fib of 1 would try and use the recursive case, and it'd be like, oh yeah, it's fib of 0 plus fib of negative 1. No, you have to give two base cases. Fib of 0 equals 0, and fib of 1 equals 1. Okay? So you need two base cases, which is weird. And in the recursive case, you make two recursive calls. That's crazy. So that was just a taste of Fibonacci. We're going to program it next time, and we'll go from there. So I'll see you in the next lecture.